All right, so we're not going to spend a whole lot of time talking about polar graphs and just generally graphing polar equations. It's something you'll come back to eventually in calculus, or you'll develop some kind of interesting tools for drawing these kinds of things. But there is one thing I do want to talk about. I want to talk about identifying symmetries in polar graphs. Remember we talked about symmetries, hopefully in maybe a college algebra class. You talked about symmetries with rectangular coordinates, right? For example, a graph could be symmetric with respect to the y-axis or the x-axis. And you have some rules that you look for, right? Some properties that you look for. For example, a function is symmetric with respect to the y-axis if for every x, f of x equals f of negative x. Symmetry with respect to the y-axis. And you had a rule, if f of x equals negative f of x, then the graph was symmetric with respect to the x-axis. Well, we've got some similar rules for working with polar graphs, right? And we have three different kinds of symmetries, and I've outlined the rules here, right? Something is symmetric with respect to the polar axis. Remember, that's the axis that starts at the pole and goes straight out to the right. Is kind of the equivalent of the positive x-axis. To test that, we replace theta with minus theta and see if we get the same thing. This is a little trickier to describe because remember, these things that we're talking about here with these polar graphs, they quite often aren't functions. So we don't have that function notation to fall back on, which is why I'm having to just kind of describe them, replace this with this, right? Symmetry with respect to the line theta equals pi over 2. That would be the polar equivalent of the y-axis. Replace theta with pi minus theta and see what you get. See if you get the same thing. And for the pole, you either replace r with minus r or theta with pi plus theta. Either one will get you the right result. So let's try this out. Let's take these out for a spin. All right, so I've got the rules down to the bottom just for us to have to look at. And I want to test this thing. What does the graph of r equals 1 plus 2 cosine of theta have in terms of symmetries? And all I'm going to do, I'm going to apply my rules, right? I'm going to check the polar axis first. And the rule here is replace theta with minus theta. So if I do that, this becomes r equals 1 plus 2 cosine minus theta. And we've got our cosine negative angle formulas, right? This is 1 plus 2 cosine theta, and that was my original formula. So this one is a yes. This function is symmetric with respect to the polar axis. All right, so how about that line theta equals pi over 2? Right, that's the positive y-axis. Well, let's see. Theta equals pi over 2. To do this, I'm going to replace theta with pi minus theta. So this is r equals 1 plus 2 cosine pi minus theta. Now I'm going to use my cosine difference formula. This is 1 plus 2 cosine pi cosine theta plus sine pi sine theta, which is 1 plus 2 times, let's see, sine of pi, that's 0, so this part goes away. Cosine of pi is negative 1, so this is negative cosine theta, which makes this 1 minus 2 cosine theta, which is not the original. Right, this is not the original, so this one is a no. The function does not have, the graph does not have that symmetry. All right, so one more. Replacing r with minus r, I don't think is going to be very helpful here. It's not going to be very easy to manipulate around if we do that. So I'm going to go with the other rule, right, to test the pole. I'm going to replace theta with pi plus theta. So this is r equals 1 plus 2 cosine pi plus theta. And now I'm going to use the formula again. 1 plus 2 cosine pi cosine theta minus sine pi sine theta. All right, so let's see. This is almost the same thing. Sine pi is 0, so this part goes away. This part is negative cosine theta, so this also comes out to 1 minus 2 cosine theta, which is not the original. So this one does not have this kind of symmetry. It is symmetric with a polar axis and nothing else. Okay. So, how about this thing, right? I want to graph this, all right? I want to graph this, and to do this, I want you to think about symmetries first. Matter of fact, why don't you pause this, see if you can run through those symmetry tests, and see what symmetries this thing has. Okay, so let's see. I'm going to try the polar axis. Replacing theta with minus theta, this becomes r equals 1 minus sine minus theta. And we know sine of minus theta is minus sine theta, which means this becomes 1 plus sine theta, which is not the original. So this one is a no. It does not have that symmetry. All right, so now let's try the line theta equals pi over 2 and see what we get. Well, my test here says replace theta with pi minus theta. So that looks like r equals 1 minus sine, pi minus theta, which is 1 minus sine of pi sine of theta plus, I was reverting back to the other formula, sine of pi cosine of theta plus sine of pi, cosine of pi sine of theta. Excuse me, that should be a minus there. Minus cosine pi sine theta. So, sine of pi is 0, so this first part goes away. And let's see, now this is 1 minus cosine pi. That's minus 1. So this is just sine theta. And I really don't need those parentheses there, do I? It's just 1 minus sine theta. So that is the original function. So that one is a yes. Right? My function is symmetric with respect to the line theta equals pi over 2. Okay, now I'm not going to make you sit through watching me do the other one. It is not symmetric with respect to the pole. If you tested that one, again, by replacing theta with pi plus theta, you should have ended up with something other than the original formula. So now, let's see. Now I'm going to pick points. Right, that's kind of what I'm down to. So here's what I'm going to do. I'm going to clean this up just a little bit. Right, so we've got room to work with here. And I'm going to make a table, right? Because that's still really the best thing we have to work with here. But notice the angles that I've picked. I've only picked angles on the right side of this line, theta equals pi over 2. And that's because of the symmetries. Once I get that side of the graph, then I'm just going to duplicate the image that I get, make the mirror image on the other side, and I'm home free. Okay, so now this is mostly a matter of going to your calculator. You can pause this if you like. Pause for a minute. See if you can work out these values, then come back and we'll take a look at the graph. Okay, so here are my results. We can take a look at a couple of these real quick. just so you can see, make sure we're on the same page. When theta is negative pi over 2, r is 1 minus sine negative pi over 2. Sine of negative pi over 2 is negative 1. So this is 1 plus 1, which is 2. Then down here, for negative pi over 6, 1 minus sine negative pi over 6. Sine of negative pi over 6 is negative 1/2. So that's 1 plus 1/2, which is 1.5. Right? So that's where my values are coming from. All right, so let's see how we can graph this. All right, so here's what I'm going to do. I'm going to distort this just a little bit to make sure we have room to really get this in here. I'm going to make this line r equals 2, which makes this line r equals 1. All right, so let's see if we can plot these. When theta is negative pi over 2, right, that's this line here. When theta is negative pi over 2, r is 2. So that's this point right here. All right, then let's see. When I'm going to jump. When theta is 0, r is 1. That's right here. Then let's see. Negative pi over 6. That's this line here. And at this point here, right, it's negative. It's 1.5. So that's going to be over here. Well, that's interesting. So it's kind of doubling back a little bit there. Okay. When theta is pi over, I'm kind of picking the ones that are easy to graph. When theta is pi over 6, that's this line. That's positive pi over 6. R is 1/2, so it's pulled back in to here. Then when r is 0, or excuse me, when theta is pi over 2, that's this line. R is 0 and is here on the pole. Okay, well, you can slip some of these other numbers in there if you like, but I really think this is enough to give me an idea of what the graph is going to look like. It's going to come here, and here, and here. There you go. Right, now, remember, there's a reason I only picked fourth and first quadrant angles, right? It's because of that symmetry we found. This graph is symmetric with respect to this line. So I can get the other side of the graph just by duplicating, mirror imaging, if you will, this side. See, I'm trying to pick a point or two just to make sure I end up being reasonably close. So it's going to be here and here. And okay, more or less, that's the graph. I've got a much better version of it here. Right, there you go. Much cleaner. That's what this graph looks like. And now maybe you understand the name, right? A lot of these polar graphs, they have very interesting, very creative, sometimes very colorful names. This one is called a cardioid, playing off the word cardiac, right? It's got kind of that classical heart shape, right? So again, hopefully you're starting to see how we're getting unusual graphs from these polar coordinates, right? And if you're following along on the website, there some of the labs are going to give you the opportunity to again kind of work through some more of these and get an idea for some of the variety that we can get from these things. Okay, so what's next? Well, we're going to continue talking about how these polar coordinates can be applied, and really we're getting to the heart of the class. I think one of the most interesting subjects in all of this kind of introductory trigonometry sequence. We're going to establish a connection between these polar coordinates and complex numbers, right? And it kind of not maybe not where you expect it to go, right? But it turns out it's a really useful connection, and it's going to let us to do some arithmetic things like taking square roots of complex numbers, raising complex numbers to high powers like 10th or 20th power in a very very straightforward way.